founded a company with his brother John, who is also a controls engineer. Together, as Peterson Brothers Automation, they spent several years investigating new ways to teach industry technicians and high school and college instructors about how to use new technology to improve efficiency, reduce costs, and create a positive workplace culture. David has also taught various control systems and robotics courses at Clark College and Portland Community College. Following the presentation, we'll have a live Q&A with David. You can submit your questions at any time during the session using the chat box on the right-hand side of your screen. Thank you so much for joining us. With that, I'll hand it off to David for his presentation.
Hello everyone. Thanks for joining us for Control Automation Day 2025, and thank you for joining this live session where we're going to explore some of the things that make modern sensor technology so versatile in the industrial automation environment. And one thing that's a little bit surprising is that the actual devices themselves that do the sensing inside of the sensor, also known as transducers, have actually evolved very little over the years. The basic elements that sense things such as light, pressure, temperature are the same integrated circuits that have been used for years, but they've been able to become smaller, more efficient, and we've added so many more features to the sensors that instead of looking at the evolution of the technology inside, instead what we're going to do is take a look at the evolution of the technology outside, or the connectivity that allows the sensors to be used effectively when built into the rest of the automated control system. So with that, we're going to have a hands-on exploration of sensing technology, but the connectivity of sensors that makes them so useful as the years go by, now that we have access to more data and more computing power in our PLCs and in our computer environments. So let's take a look. The first thing that we need to be aware of is what makes sensors so important in the industrial automation environment. Well, in the first place, sensors are the first entry point of data into the system. Without sensors, we can send commands out, we could tell motors what to do, we could tell conveyors how to run, but we have no way of bringing back any information. These days, not only are we interested in the data that can control the process, the things that turn on the air valves at the right time or run the motors at the right speed, those are all really still very useful for building the products, but we're also now interested in how can we collect data that tells us over a long period of time how are things working. Not just how is the process itself working, but how are the devices working that are running the process. All of that is part of the data collection that we now use, and thanks to huge amounts of data being able to be brought in from the system and the shop floor, we can handle that much more effectively. But we don't always need to look at the most complicated and fancy setup. Some of these sensors are purely pieces of information that are giving us critical looks into what's happening in the system. Examples of sensors that are really common are things like presence sensors. We also call them proximity sensors, temperature sensors, weight sensors, pressure sensors, voltage sensors, current sensors, flow rate sensors, distance sensors. Pretty much if there's a quantity out there, you can probably find a sensor that's going to measure that quantity and give you back some information about it. But again, how do we connect that sensor to the control system? Well, that's a bigger question because there's so many different ways out there. So we're going to break this discussion into a couple of different segments. First, we're going to look at the pieces of connectivity, the signals that actually connect the devices, the sensors themselves, to the control system. But we're also going to take a look at some of the protocols, these fancier communications that are becoming more common, that may not be present in the sensors themselves, but are part of the sensor and field device network that can allow everything to work more efficiently in the field. Really what it comes down to is, what do we need? How are we best going to connect those devices that we need? And how are we going to keep ourselves from having to maintain a really complex or very expensive system later on? Only designed for what we need. So with that, we're going to start with some of the most basic sensors that you can find on the market today. These first kind of sensors only provide a single direction of communication, single directional, from the sensors to the controller. And the most basic one are simple switches. Mechanical, or sometimes we refer to these as electromechanical. And what electromechanical means is that there's an electrical element. Obviously, we need to allow current to flow through the sensor to send its signal off to the control system. But there's also a mechanical component, which means something is physically moving inside. A lot of sensors these days have no moving parts. They use some form of semiconductor, which we'll get to in a minute, to be able to sense the environment around them. But these electromechanical sensors are still really important. What are a few examples of these? Well, here's some examples. The electromechanical sensors can include things like selector or quarter-turn rotary switches. They can include push buttons, safety push buttons, or non-safety, just simple push buttons. They can also include limit switches, and they can include relays. The electromechanical relay is a very common device that is an output device, but it's also meant to send information off to something else, and sometimes these relays form part of the control system themselves. One common factor about all of these electromechanical switches is that there's some sort of moving part involved. We can hear a click, we can feel something move, and that mechanical motion means that inside a piece of metal is simply touching another piece of metal. Could be due to an electrical coil, it could be due to, like with the limit switch, some sort of external force applied on the side of it, and that gives us that motion that we need, and often accompanied with a click sound that we can hear to assure us that the sensor is actually doing its job. But a big question that we'll address with all of these sensors is, how do they work? How do they actually get connected to the control system? Well, mechanical switches, these simple, very simple electromechanical switches, are probably the easiest ones to connect, and they're the most versatile. They have some weaknesses, but we'll get to that in a second. The main way that we connect these is we look at any one of the what we call contact blocks, which is the actual part of this switch that's making contact. For all of these switches, I can expose two screw terminals, and these two screw terminals allow electricity to flow in and electricity to flow out. So what do we need to connect it? Well, really all we need is just two wires, one for electricity to flow into this physical contact, and another one for it to flow out. When we connect it to the control system, what we're going to look for is a digital input module. That digital input is going to either allow current to flow in, which is what's called a sinking input, or it sends current out, which is what we call a sourcing input. The great thing about these electromechanical switches is that they don't care which direction electricity is going, either coming from the module or going to the module. As long as we connect our power supply properly, there's no such thing as a polarized mechanical switch. And therefore, we can hook them up either direction we need to fit the constraints of the control system. Even these devices like limit switches. When we open the cover on a limit switch, we can see sets of contacts inside, each identified by pairs of contacts. Two in each case, one to allow electricity in, one to allow electricity out. Sometimes we'll even be given both normally open and normally closed contacts, which is common in limit switches and in relay contacts, so that we can choose the most appropriate connection method for our system. So what's a huge advantage of these, or where are they used? Well, since there's no circuitry inside, first, we can use it safely with many different voltages. We don't have to worry about whether it's designed for 5 volts or 12 volts or 24 volts. They're compatible with most all control system voltages. Now, not all control system voltages, because there are some control systems that can operate at 230 volts or even higher, so we do have to kind of look at those data sheets and make sure that we're not providing too much voltage, because of course we don't want to damage anything. Another great advantage is that there's no adjustments. Now, for some situations that may be a disadvantage, but for these electromechanical switches, it means that we can safely go to the storeroom, replace it with a drop-in component, and we don't need to worry about configuring any settings or adjusting any parameters. Just drop it in, and it's 100% consistent and never needs to be changed. Like I said before, a third benefit is that we can use them in any kind of control system, whether it's an NPN or PNP, which is that sourcing and sensing. That's going to come up in just a second in our next category of devices. They're not so flexible in that case. But with these electromechanical components, since electricity can flow either direction, we're safe and we don't need to worry about whether that electricity is polarized or not. The next category of switches that we're going to look at are 3-wire sensors. They still provide single direction data flow. That is, the electricity only flows between the sensor and the controller. It's meant to convey a signal not any further information to the sensor, but they're a little bit more complex in the way they operate as compared to the switches. So here's a few examples. We have here a number of sensors, and these sensors have usually either 2, 3, or 4 wires, with 3 being the most common. 3-wire sensors is a really common term to hear in industry for this reason. These provide more than just the simple metal contact on-off action because they can be divided up into a couple of different categories. The first is discrete sensors. These discrete does mean on and off, which means that we have a certain threshold or a set point at which we want that sensor to trigger. Perhaps if that's a distance sensor, what that means is that when an object gets close enough beyond a certain threshold, that on-off signal is generated. Now this is different from what they call a distance sensor because a distance sensor will always return the distance that object is from the sensor, and that number is constantly changing. So we often refer to these kind of sensors as switches, a distance switch, a temperature switch, because they switch their states on and off between a high and a low around a certain threshold. A couple of ways that these might look, because again, what we're really interested in here is not just what these do, but we're really interested in how they work. That's one of the keys to engineering and what we want to talk about here today. So let's take a look at a couple of different scenarios. First, there are 2-wire sensors. These 2-wire sensors, in this case, an inductive proximity sensor, which can sense metal, they provide an electrical flow between positive and negative, or in this case is an AC sensor, between a live and a neutral wire, and that provides the voltage required to create an oscillation of a magnetic field in the sensor. And when the presence of ferrous metal comes into that sensor's field of vision, it changes the electrical field and turns on a switch inside that can provide that signal out to the PLC. A bit more commonly is these sensors that are called 3-wire sensors. It's a bit of a misnomer here because 3-wire sensors might actually often include 4 wires, but 3 of them are the most critical. Let's talk about those 3 wires in these distance sensors or optical sensors, proximity sensors, this whole wide range. These 3 wires have the function first of providing a constant positive and negative voltage. Providing a constant positive and negative voltage means that inside the sensor we can power some electronics. Unlike the 2-wire sensors, which until the physical circuit was completed when you push the button, there's no electrical flow, if I have positive and negative supplied to this sensor, I can power semiconductor electrical circuits inside. One of the most common semiconductor ones is an LED. You'd see an LED that would indicate the presence of no object, and it would also indicate the presence of an object. Well, how would it get enough voltage to be able to run that LED if there was no voltage supplied from both a positive and minus source, regardless of whether the object is there or not? So for that reason, we provide a plus and a minus, which come directly from the power supply. So that 3rd wire in our 3-wire sensor provides our sourcing or sinking voltage, like we discussed before. Sinking means the electricity can come to the sensor from the PLC. Sourcing means that it goes to the PLC from the sensor. Another way that these are termed is that a sinking sensor is also called NPN, based on the transistor technology inside of it, and a sourcing sensor is called a PNP, also because of the transistor technology inside of it. Now what about these 4th wires, sometimes even 5th wires? Well, a 4th wire can take on a variety of different uses. I have here one sensor. This is an optical proximity sensor. One of the wires, aside from our typical plus, minus, and signal, we have an extra white wire. This white wire's function, whether it's tied into the plus or the minus from the power supply, changes whether this is a normally open or normally closed switch. So it's a great way to be able to buy one switch that can be used in either situation. You just have to choose what to do with that last white wire. Another sensor, this one is another optical sensor from a different manufacturer. It also has 4 wires, but in this case the 4th wire is used to send a couple of pulses to be able to teach the sensor what is an acceptable range or window of operation for the object that's coming into its field of view. Some sensors have buttons or potentiometers that we can adjust, but it's great to be able to install our sensor, and if something needs to be changed, we don't have to walk up and push on the back of the sensor or find a screwdriver and change it. We can simply send a signal remotely. So there's a lot of different uses of that fourth wire depending on the datasheet's value. So it's always really important to take a look at those datasheets before we decide for sure which sensor we're going to need. But the three most important are the constant positive and negative voltage, but then also that NPN or PNP signal that's the communication between the sensor and the PLC, and that's part of what we're talking about today with one of the most common connection technologies across the world of sensors. Now, are there any advantages to this over mechanical sensors? Well, if mechanical sensors are really simple, really versatile, why would we ever use a more expensive, more complicated, requiring more wires for a sensor when a mechanical one would do? Well, in some cases, there is no sensor that, from a mechanical perspective, can sense distance. Now, we do have linear potentiometers and a few exceptions to this rule, but for the most part, there are many non-contact systems that are greatly benefited when we can take advantage of something like light. Light will not apply a physical force on a switch to be able to cause an electromechanical contact. So there's many of them that simply we need a semiconductor solution, and a mechanical solution is not going to sense the quantity that we need. Also, that adjustability and flexibility, like I said with the mechanical sensors, sometimes that's nice to not have to change anything, but it usually is better for a well-optimized system to have sensors that we can adjust when needed. Also, that status indicator can be a great troubleshooting tool. With very few exceptions, some exceptions being some relays have lights when a coil is energized. Those ones tell when it should be activated and not. But for the most part, most electromechanical sensors do not have any sort of indication to tell what state they're in. So when we are looking and diagnosing a faulty sensor, how are we supposed to know if it's working or if it's not? With these semiconductor or three-wire sensors, very often an LED will show us whether it's currently sensing or not sensing, or whether it's outside of an acceptable range and sending back an error, and it can immediately pinpoint a problem. Much faster for troubleshooting, and even a few minutes of saved downtime can easily pay for the sensor. Another benefit is the long life of semiconductors. Now, these mechanical switches, in this case, a push button, it's meant for an operator. It's probably going to last well beyond the lifetime of that system, as long as it's kept within a reasonable, not being too much force applied to it or too much humidity, having water dropped on. As long as it's used correctly, under the right conditions, it's probably going to outlast that machine. But that's because it's not being pressed very often. For some of these sensors, if they're repetitively being sensed over and over and over again, that mechanical life cycle would be reached very quickly, and you'd constantly be having to replace that sensor. Semiconductors with no moving parts last many times longer, and therefore the service life of a high-speed sensor is much longer. Are there a few cautions to these? Well, absolutely. With the mechanical switches, we could apply whatever voltage up to a maximum allowable, and everything below that was safe. With these three-wire sensors, they're going to need a certain amount of voltage to run the electronics inside, but if you provide too much voltage, you can destroy them. So a very common voltage for DC sensors like this is 10 to 30 volts DC. So a 12-volt system, 24-volt system, those are great. Apply 5 volts, it's not going to be enough to run the sensor. Apply too much, say 120 volts AC accidentally, and you will destroy the sensor. So we have to be very careful about those parameters. Also, the mechanical switches were non-polar. You could apply electricity in either direction and it was fine. But with a three-wire sensor, we have to be careful to look at the NPN or PNP output to make sure that it's compatible with the control system. Quick hint here is if we have a PNP sourcing sensor, that's got to be used with a syncing input. They must be opposites. So if we have an NPN syncing sensor, on the other hand, we have to use a sourcing input module. So it's often the input module that dictates what kind of sensors we need. Although that depends on which came first, the sensors or the control system. But the sensors are a lot cheaper, so often they are going to be chosen based on what the PLC itself needs. So these are a couple of the most basic forms of sensors to provide digital or discrete inputs, that on-off signal that goes between the field and the control system. One other that's worth mentioning here, mostly because it's very similar to the digital 3-wire sensors, is analog sensors, sort of the complement of digital. Analog means that instead of providing that on-off threshold, it means that we're providing a whole range of voltages or currents. 4 to 20 milliamps is very common. Also 0 to 10 volts is very common, but there's exceptions to that. That provides an entire range between a minimum and a maximum of sensing distance. So let's take this optical sensor, for example. In this optical sensor, it may trip at about, say, 300 millimeters, or about a foot, 300 millimeters. That's great for knowing if an object enters that field of view and is closer. But what if we wanted to tell the difference between 3 or 4 different sizes or distances of objects? We'd have to buy 3 or 4 different sensors, each of which has a different threshold. That would be much more expensive than finding an analog device or an analog sensor which can sense and provide a voltage that swings between 0 and 10 volts the entire time it's scanning. So in those cases, a little bit of a difference here is that we don't have any adjustments to those sensors. We don't have a control knob or a potentiometer to be able to adjust the sensitivity of an analog device. You buy it and the data sheet says 0 to 10 volts is a window between this range and this range. All of those adjustments, the thresholds, things like that, those are all done in the software. Since we can return back any value we want, we simply allow the software to compare the current value to a threshold value that we want, and then energize output devices based on that. What sort of quantities can we measure with an analog sensor? Basically any kind of quantity that's variable in real life, which is most real life situations. Temperature, pressure, even colors, weights, distances, all of these different quantities are able to be measured, usually again by some sort of a semiconductor, so the long life, very energy efficient, and that can convert that physical quantity into a voltage or a current quantity, which is then sent back to the PLC. What kind of module do we need to get an analog sensor to work? Well, we need an analog input module for our device. There are a few different kinds of analog sensors, but for the most part, our explanation of those 3-wire sensors for the discrete outputs applies to analog as well. If we look at the wires of an analog sensor, we will see a couple of different wiring schemes. We see 2-wire analog, 3-wire analog, and 4-wire analog. All of those are fairly common, but they actually are not different from each other. They're exactly the same. They just get there a slightly different way. So first of all, 2-wire sensors do require a separate power supply. The 2 wires only are the data communication off to the PLC, either the current or the voltage. Separately, that sensor is going to be supplied with a positive and negative voltage from a power supply. So it really still has 4 wires, but we're only concerned with 2 of them as far as the PLC goes. 3-wire sensors actually operate exactly like 3-wire digital sensors, the discrete ones. We have a plus and a minus to supply the internal working voltage for the sensor itself, and then the 3rd wire supplies the current or the voltage that we need. Finally, we have 4-wire sensors which receive both their power and their signal wires from the PLC. There's a couple of different ways that analog signals can travel. Either single-ended, which means we send a signal off to a PLC, but we also have what's called differential current and voltage signals, which means the 2 wires are compared against each other to tell the difference. One of the cool things about this differential signaling is that let's say that it's traveling a long distance and somewhere along the line it runs past some sort of machine putting some inductance into the wire and the voltage spikes really quickly. Well, what the controller is going to see is that spike in voltage. It doesn't know the difference between a disruption in the wire, some interference, or a change in the actual signal. What was the reason for that? But if we have 2 wires being compared against each other, the difference between them, and they travel past this machine, they're both going to see an equal spike at the same time. But the difference between them has stayed the same. So we know that that was due to some external interference, and by the time it reaches the PLC, the end device, there is still no difference between the wires. The only differences would be caused by the original sensor outputting a difference between the voltages. So it's a really clever, creative way to minimize some of the electromagnetic interference. But we do also have to be very careful about voltage versus current when we're selecting analog inputs. Some modules can be selected either way, but a lot of modules cannot. So if we have an AI module, the AI part number may have a 1 or a 2 or a version A and B or slight revisions in that part number that tell us the difference between voltage and current, and we need to make sure to choose the right one based on the sensor that we've got. So are there any advantages to this over discrete sensors? I think the answer is probably pretty obviously yes. We can have an analog sensor that can accomplish a lot more than a discrete sensor, but we do have to remember that they take extra modules, or if they're built in, they're going to be fewer built-in analog input modules for a PLC, so they tend to be more costly in a system. Instead of simply having one address in the PLC devoted to a trigger that's on or off, very simple, very easy to diagnose, we have to do everything manually in the programming when it comes to analog sensors. And sometimes that can create a much more complicated program, or unnecessarily complicated if we don't need it. I mean, if they were completely better than digital in all aspects, then we wouldn't have digital sensors, we would only have analog, but that's not the case. We only design for the system as we need it. We can also have systems with more than one set point for a single quantity, and that's really important, something that the discrete sensors cannot give us more than one set point per sensor. Analog can do that, and a couple of others that we're going to talk about here in a little bit. They can provide us more information. Do we want to track data for a process? Or do we want to track data over a long period of time to tell us what might be happening, what might be deviating from a normal thing? Let's take an example of a box on a conveyor belt. Now the sensor is supposed to trip every time a box goes past on a conveyor belt. Well, we could use a discrete sensor for that. It's easy. We just make the adjustment to the right point, and the sensor is going to trip every time a box goes past. But if we use an analog sensor, let's say that over a period of time we notice that the boxes are starting exactly 4 inches away from the sensor. But over a period of time they start increasing 4.5 inches, 5 inches away, 5.5 inches away, and slowly over time, potentially due to some mechanical wear, the tracking of the belt on the conveyor, something is causing that box to get further away. The discrete sensor wouldn't tell us that. But with analog data collection over a period of time, we can still make the system work the way it was supposed to. Yeah, it was still over 4 inches away, but we can take a look at those changes and say, something might need to be looked at in this system, just in case there's some problems. So analog absolutely has a lot of benefits over digital, can certainly be used in a lot of cases, but if it really is unnecessary, it is an extra expense both in modules and in sensors, and complexity in programming to be able to use them effectively. Now we've reached the end of the sensors that send information one way to the PLC. But we haven't reached the end of different kinds of sensors. We haven't even come close. And now we're going to discuss a second category of sensors where information can now travel both directions. Not only can information travel both directions through some of these strategies, but we can get a lot more kinds of information rather than just whether something is on or off, or just the simple analog quantity by itself. The two most common standouts in this area are a couple of protocols. One is slightly older and it's called HART, Highway Addressable Remote Transducer. We'll talk about this in a second. And also IO-Link. IO-Link is one that has been around for a little while, but is becoming extremely popular in connecting all kinds of different devices. A few others that are used in this sort of sense are not found commonly in PLCs, but they are found very commonly in lots of other types of controllers, and they'll have names like I2C or I2C, SPI, the serial peripheral interface, or UART, a universal asynchronous remote transmit, where you see a TX and an RX, sort of like a USB. These are very common in, again, those microcontroller, small system on a chip or single system on a board kind of computers, not as common for PLC protocols. So in our discussion today, we're just going to stick with the ones that are more common to PLC. So with that, let's talk about the first one, and that's called IO-Link. I've got a couple of IO-Link devices here. And one of the benefits of IO-Link, like I said, is the ability to be able to send data two different directions. So it can handle a few different things. First of all, we can still set set points. We can determine those set points, and we can receive a digital signal, which is input information based on the process, just like those discrete sensors. We can send it a command and say, I want you to tell me if a box is more than 4 inches away between this, and send a high signal. And it will. Great for a replacement of a discrete sensor. But it can also, at the same time, be sending us those analog values. It is rare, but possible, to find both analog and digital sensors in the normal 3-wire type of arrangement, where the 4th wire is the analog signal and the 3rd wire is a settable discrete signal. But those, although they provide a bit more flexibility, still fairly limited as far as sensors go. I/O link is that two-way communication where we can, from the controller or from the computer, we can send all of the set points, all the configuration information, lots of different details to the sensor, and we also have record of everything that's going on all the time. Multiple set points, analog, discrete set points to be able to determine what configuration the sensor is currently set in. Like with these sensors, the 3-wire sensors, once you set a position or teach a position to it, nobody really has any idea without testing what these positions are. But with I/O link, we can read all of the data that's been previously saved to a sensor, saving us a lot of time. If we need to replace that sensor, duplicate a system, we can just copy all of those parameters into a new sensor. There's a couple of examples of I/O link devices. Here is one that is an optical distance sensor. It will return back my distance as an integer. And I also see on the top, I see these notations for Q1 and Q2. Not only can I set these and allow the sensor to act as a discrete sensor with 2 output set points, that's pretty cool, but I can also use those 2 individual set points as part of my I/O link data package, creating a sensor that can send a lot of different signals depending on how we want to use it. That is one of the nice things about I/O link sensors, is very often they will also have the capability to act as discrete sensors, so you can use them as replacements into your system even if you don't yet have I/O link. Here is a distance sensor that's a magnetic distance sensor that's designed for attaching to the side of a pneumatic cylinder. So it'll give me limits and settable limit points, so that not only does the cylinder need to travel all the way to the ends, but we can set trigger points at any point that we want and receive the analog value that tells the current value of the cylinder's position at any time. This one also has a complementary analog output, which means it can act as I/O link or as an analog sensor so that my PLC can receive that information. I also have a pressure sensor. This pressure sensor has a minimum and maximum, but it also has all of the previously discussed data, different set points, the analog value, being able to set parameters, being able to read the previously set parameters between the device and the control system, giving us a much more flexible system. It is more flexible, but that also means, and usually means, that it is a bit more complicated. So what do we need for an I/O link system? Well, right behind me on the wall, I have an example of a device. This device is called an I/O link hub or master device. This one's actually programmable to be able to accomplish quite a few different tasks, but usually what we're interested in is a device that they refer to as a master device, which connects to a PLC through a field bus communication like Ethernet, Profinet, something like that. And then each one of the sensor connection pins can be either digital inputs or outputs or I/O link data, which can send information out or in. Interestingly, this light behind me is also an I/O link device, and we can choose the colors, the speed that it's changing, all kinds of information from that. Although our discussion today is primarily focused on sensors. Each one of these connections is an M12, and that M12 is a 5-pin standard connector, and we see on the other end, the sensors have exactly the same kind of connection. So that means that we can connect this with a standard M12 cable to be able to connect our I/O link devices to the I/O link master. We will also then need a communication cable, that field bus cable, Ethernet, Profinet, EtherCAT, to be able to talk between the I/O link master and the PLC. So it does introduce a little bit of extra hardware in this kind of complex, somewhat costly device that goes in between. but the speed with which we can expand a system, change a system, upgrade a system later on is a great way of future-proofing, especially for those kind of systems which are in the design phase right now, the greenfield kind of systems where we could dream. If we want whatever we want to be able to someday collect all the data about our process, analyze it, and look for weaknesses and defects and optimize it. Well, we might consider looking at some system that can collect more data than you need right at the beginning, but provides you an easy opportunity to increase the amount of data you're getting later on. IO-Link is a brilliant system, a brilliant protocol setup, but it does have a little bit of a learning curve. So we have some tutorials available, and we've done a lot of work with companies developing IO-Link on control.com, so I encourage you to check those out if you're interested in learning more. A little bit of a shameless plug for our content there. The software side can also be a little bit more complicated because with analog and digital inputs, the only thing we need to worry about is the value of the tag in the PLC. It will be either a 1 or a 0 for discrete, or it'll be an integer value for analog. But when it comes to IO-Link, we have to be able to apply an EDS, an electronic data sheet, or a GSD file, which is a Profinet equivalent of the ESD for Ethernet. We need to apply those to our PLC, which tells it when I see a packet of information coming across the Ethernet line or Profinet line, how am I supposed to translate it and drop it into the right tags to give you access to the data? That's something that you very, very difficult to just guess and check until you find the right thing. You also can install what's called an IODD or an IO-Link device description file on the IO-Link master, which can allow you to configure some of the parameters right on it. Some of these IO-Link devices have web servers built into them, so you can do some programming directly on the IO-Link device itself. So we have a few more levels of complexity here, not just in the hardware setup, but also in the software. But with that complexity comes a lot more capabilities as well. Now, the next one of these device protocols that's connected directly to the devices is what's called HART, Highway Addressable Remote Transducer. And what this protocol is it's a digital signal that's superimposed or dropped right on top of a 4 to 20 milliamp signal. Now, it doesn't happen with just a standard analog input. So you do have to have a HART input module or a HART communication module for your PLC, but it is a two-way communication that can allow you to read information and determine set points on the sensors, very common in process control like flow rate sensors, temperature sensors. HART is a very common protocol in these kinds of process industries. But we can send values, we can also calibrate sensors remotely, which is also very important for these analog process control values, which have to be very carefully monitored, and calibration is a big deal. But these HART devices are meant to provide bidirectional communication. It's the digital input, digital signals on top of the 4 to 20 milliamp. The PLC and the device at the ends can filter out the two, with the analog signal still referring to the process data that's being transmitted, but the digital signal a pulse train that provides digital information, much like a standard digital field bus, like Ethernet or Modbus or something like that. Now, speaking of Modbus, that takes us to another kind of protocol, and it's a little bit of a variation from the last ones that we talked about. This one still is two-directional, but instead of the devices themselves connecting with this protocol, we're moving up a level, and this is what we'll find connecting between these hubs or remote I/O devices. Another example of a remote I/O device behind me here. Between this and the PLC, sometimes some very unique applications and protocols take place. A couple of them that we're not going to discuss, just in effort of time, is things like Ethernet and Profinet, these more universal field buses that are used to communicate all over. We're going to stick with the ones that are just used for sensors and traditionally have been around for the application of sensors in the past. So the first one that we're going to talk about is Modbus. That's actually what this one is communicating over. Modbus is a system of being able to read and write discrete bits, which are on-off values, and analog values, which are usually called registers, meaning that they can be any sort of integer information, even if it's not an analog input. But we can transmit those with a very consistent set of commands. And what usually happens is this Modbus command and address, so we send a command, what do you want to do, and where do you want to do it to? I want to turn a bit on, and I want to do it in this location or at this address. So we send a command and an address, and those are packaged into another kind of device protocol, a carrier, if you will. Now, these carriers, most commonly that we see today, are Modbus TCP, which is a variation of the transmission control protocol, much like Ethernet, so they look a lot like an Ethernet port. But we also have Modbus RTU and ASCII, which are very commonly transmitted over RS-232 and RS-485 connections, RS-232 being a serial connection, RS-485 being a twisted pair multi-drop kind of connection. Those two will, although we don't have time to explain these thoroughly in depth, those two are going to show up quite often in looking at these protocols that were initially designed to be able to communicate between devices in the field. These registered standards 232 and 485 were very common for transmissions to be able to be sent from a device with data and to a device to ask questions, pull for information, or send configuration information. So again, depending on the carrier that's in play, the Modbus commands, which do not change, can be wrapped into a data packet to be sent over Modbus TCP or Modbus RTU or Modbus ASCII format. A lot of controllers with multiple communication headers can accomplish any of these communications. Not very many individual sensor devices have Modbus built into them, which means that often what we're going to be doing is sending Modbus communication between the PLC and a remote I/O. That remote I/O is going to be connected to the discrete sensors and the analog sensors. So it accomplishes the task of data transmission, but not by connecting to the sensor directly. That's what I mean when I say we've kind of reached a third level of bidirectional communication. Another one that is popular in some areas is called the Actuator Sensor Interface, or ASI. This one is a bit more simple in architecture than Modbus because it uses only a keyed two-wire communication between a gateway, which is a device that again connects between a one protocol level of sensor and a higher level, which means the PLCs level. So it might be converting Ethernet or Profinet to this ASI, Actuator Sensor Interface level. Each one of these, the wires, is able to be connected to what's known as nodes, not sensors. This one again does not directly connect to the sensors, but it connects to the nodes. And these nodes usually contain a couple of M12 plugs that you can connect the sensors to. Depending on the different version that you've got of ASI, some evolutions have taken place, with ASI version 3 being capable of 4 bits per node, which is great for 4 pieces of data, and it can be output or input data. So you might see a node that clamps right on top of the cable with 4 M12 connectors, one for each sensor or perhaps a relay or a contactor. Moving up to ASI 5, each node has 16 bits allocated, so that means that we can have a node or a clip-on hub that can have up to 16 individual bits. One of the benefits of ASI is the speed that it can travel with. So instead of being burdened down by all the other network traffic, we can devote this ASI to being able to connect all the actuators and sensors along a particular stream of the device to be able to come back and devote one packet with one packet interval back to the PLC. That's one of the reasons why having a devoted network just for the field devices can be preferable over simply connecting a whole bunch of Ethernet I/O modules, which ultimately would accomplish the same task, but with a much higher delay in the amount of time that the traffic takes. So we're trying to make it more efficient and more reliable without lost information, while still making it easy and achievable to be able to create a sensor network. Another one to talk about is one that's called CAN bus, or Controller Area Network. This one was originally developed as a vehicle standard, and now we see a variation of that showing up in nearly all vehicles produced since the mid-90s, which is the OBD2 interface. But all the sensors that are connected to the control module were connected with this Controller Area Network, or CAN. CAN can provide a lot of information at really high speeds. It usually uses a variation of RS-485, but it can exceed the speeds of a normal RS-485 connection, so that makes it great for some of the more complex systems. Vision systems being a very common one for CAN or CAN open protocols because of the huge amount of data that can be transmitted up to a really high speed, which is beneficial for those larger systems. A camera is a bit of an exception beyond all the other sensors that we've talked about because while it is in theory a sensor of its own, the amount of data of each pixel is so creates such a tremendous package that we can only use it with protocols that have an extremely high data rate. We'll never see an analog camera except in the most basic senses of the word. Finally, the last one that we're going to talk about today is what's called Profibus. I want to be careful that Profibus is not confused with Profinet. Profinet is an industrial Ethernet variation that's made for the process field industries. Profibus, on the other hand, was built again on an RS-485 system, multi-drop, which means a single line of twisted pair wire that has nodes or individual devices built into it. Profibus is something that can connect to remote I/O nodes, but it also is installed in some process devices like temperature sensors, flow control sensors, and so these ones are found in both the sensors and in the hubs themselves. One of the major advantages of this over some of the others is, again, its high speed, up to 12 megabits per second, which is a bit higher than the normal 10 megabits per second that RS-485 is technically rated for. So both of these last two protocols can provide much higher data rates, which is really beneficial for process automation. So as a wrap-up summary, we looked at some of the basic I/O devices, these switches, electromechanical, which means when you push a button, you apply force, you hear a click, you feel something move. What's happening is a piece of metal touching another piece of metal, creating a switch contact, much like a light switch, and allows electricity to flow, and that provides the most basic form of input sensing for a PLC or a control system. We also looked at some of the 3-wire discrete and analog devices. These can provide a bit more information than just a mechanical switch clicking on and off. They can provide variable information that then we leave it up to our programming skills to decide what are we going to do with this information. But as modern technology has evolved, and that's happened over a long period of time now and will continue in the future, we definitely need more data and we need it faster, so that's where these communication protocols come in. We also need to be more flexible and change things on the fly. That optimization means tweak something, change it a little bit if it's not quite right. So we looked at things like IO-Link, Modbus, HART, Profibus, ASI, CAN bus, all of these protocols that are designed specifically for a sensor level, a field device level, and other protocols that are built on top of these that are dedicated just to providing that sensor interface that brings data into our control system. Which is better? Well, we can't say which is better in automation. We very rarely can. If we have the luxury of being able to afford a better system, then yes, we should look to the future and say, what can we install into this system that allows us to not only control but also collect data and make things better? If we don't have that continual luxury or a greenfield application, we can still look at some of these hybrids, the ones that, like IO-Link, allow us to replace a discrete sensor with another sensor, but they also provide the ability to be able to collect much more information and change things as we go, so we can continue improving the system over time. So I encourage you to look at your system, decide what fits the best for you. It is really critical to know and understand things, and for that, again, I encourage you to visit some of the resources we have on control.com. But nobody ever can know everything about sensors. So I also encourage you to reach out to representatives and technicians and real engineers who can give you real guidance on things that they have experience in. And decide in that case, with actual demonstrations and actual examples, what's the right fit for you in your application. From here, we're going to move on to a question and answer time, so I encourage you to ask your questions. We'll answer them to the best of our abilities and hopefully help you become a better engineer with a better understanding of some of these I/O devices. Have a great day.
All right. Well, thank you, David, for that great presentation. I really learned a lot myself, actually, and we already have several good questions, but there is still time for everyone to submit some more questions. So, David, you ready to answer some of the questions we have in our queue?
Absolutely.
All right. The first one starts with a nice note from Andrina. I hope I pronounced the name right. Great session. Then asks, what software suite is best for the best software model to recreate the hands-on? So I think they're wanting to kind of model